Dear students, after studying this module, you shall be able to know about the significance of atomic emission spectroscopy, instrumentation and application of the atomic emission spectroscopy. Atomic emission spectroscopy (AES) has long been an standard method for metal analysis. Recent developments in the non-combustion plasma sources have expanded the number of applications and generated new interest in AES. There are few restrictions on the samples. They may range from alloys to ores or from ashes to organic materials to the atmospheric dust. In atomic emission spectroscopy, a minute part of the sample is vaporized and thermally excited to the point of atomic emission. The energy required for these processes is supplied by an electric arc or spark, or more recently by the laser or plasma composed of inert gases. It is convenient to distinguish these sources from the chemical flame sources used to obtain emission spectra. The atomic spectrum emitted by the sample is used to determine its elemental composition. The wavelength at which the intensity measurement is made identifies the element, whereas the intensity of the emitted radiation quantifies its concentration. Instrumentation of AES may be divided into three major components: the sampling device and source, the spectrometer, the detector and readout device. The sampling device and the source depends on the type of sample and the analytical data desired. As the emission spectrum emerges from the source, it is focused into the spectrometer entrance slit, where it is dispersed into the component wavelengths. The optical elements permit site selection within the source's discharge and thus eliminate the need to move the entire source assembly. The use of mirrors, properly placed, also eliminates the chromatic and the spherical aberrations encountered with the lens optics. At the exit slit of the spectrometer, the radiation is sensed by the photodetector. In older instruments, photographic films was used to record the spectra, but most modern systems use photomultiplier tubes or diode arrays linked directly to the computer-driven data processing systems. Given figure indicates and shows the instrumentation for the atomic emission spectroscopy. Sampling device and sources. No single source is best for all applications. In general, for solid sample arc excitation is most sensitive, while spark sources are more stable. Plasma sources are of the choice for solution and for the gaseous samples. This sensitivity enables trace analysis to be carried out at the parts per billion level. Electrical discharges. Electrical discharges can be used as excitation sources. When the discharge strikes the sample surface, it produces high current densities that volatilize a certain amount of sample. Atoms in the resulting vapor are then excited by collision in the discharge plasma. Direct current arcs. The simplest electrical discharge is the DC arc between the two electrodes. Typically, one electrode supports the sample while the other is the counter electrode. The DC arc consists of a high current 5 to 30 ampere, low voltage 10 to 25 volts discharge, usually operating in air. Arc temperature ranges from 4000 to 6000 Kelvin. Excitation of the sample atoms by a DC arc is thus both thermal and electrical in origin. The resulting plasma of the high velocity ions, electrons and atoms produces the atomic emission spectra. The DC arc as the excitation source is the commonly selected for the qualitative survey analysis of trace and major elements, metals, alloys, plastics, rocks, minerals, soils, biological materials such as tissue, bone and fluids. An internal standard can be used to minimize the effect of arc instability and the sample matrix. Alternating current arcs. Alternating current can be used to produce an arc. AC arcs are operated in either high voltage of 2200 to 4400 volts or low voltage of 100 to 400 volts region. In both the situations, the arc ceases at the end of each half cycle as applied voltage drops below the value needed to maintain it. The high voltage AC arc, the plasma spontaneously ignites during the next half cycle when the applied voltage exceeds the voltage required for the dielectric breakdown of a gas between the two electrodes. In low voltage AC arcs, the low voltage high current spark is used to initiate the arc in the next half cycle. High voltage alternating current sparks. The high voltage AC spark discharge provides the greatest precision and the stability of all the electrical discharge sources. It is the method of choice for AES analysis of ferrous metals in the industrial operations. Sparks contain high peak currents and the power density, which results in the population of high energy electronic levels of atoms and also more extensive ionization than found in the arcs. Microprobes. The laser microprobe is well suited to analysis of very small samples of tiny localized areas on larger samples. An optical pulsed ruby laser is focused via a conventional microscope onto a minute area of the sample after visual focusing has been used to select the sample area. The intense heat of the laser vaporizes the small amount of the sample, leaving the hemispherical crater about 50 micrometer in the diameter on the surface of the sample and produces plasma. Once formed, the plasma absorbs radiation from the laser beams, thus stopping further vaporization of the sample surface. Although emission spectra suitable for analysis can be produced directly with the laser sources, cross excitation with a spark discharge results in an improved resolution of spectral lines and an increased signal to noise ratio. The vapor plume generated by the laser is passed between two closely spaced electrodes that are charged to high voltage. The electrode gap breaks down, producing a spectrum similar to that produced by the spark source. The laser microprobe furnishes a tool for examining the interior of individual cells and can even be used for the living organisms. Since it is essentially a non-destructive method because of the small amounts of the sample consumed. It is also useful in analyzing the inclusion areas of alloys or corrosion spots on metal surface by those interested in these conditions. Resolution of the laser beam is currently limited to 50 micrometer by the lenses used to focus the laser beam. Non-combustion plasma sources. Non-combustion sources improve the accuracy, sensitivity and precision for the large number of elements over that found with the electrical discharge sources. Handling liquid and gaseous samples is much easier with these plasma flame sources. The higher temperatures and cleaner chemical environments of plasmas overcome two problems associated with the combustion flames: lower temperatures and reactive chemical environments. Plasmas retain the convenience of liquid sample handling and the precision of the excitation conditions characteristic of flame sources. Inductively coupled plasma sources. The inductively coupled argon plasma ICAP or ICP torch is a special type of plasma that derives its sustaining power by induction from high frequency magnetic field. Initially, argon gas passes through a 25 mm quartz tube and upon emerging at the tip is surrounded by an induction coil. An AC current flows through this coil at the frequency of about 30 MHz and power levels of about 2 kilowatts. An argon gas stream the support gas that enters the coil is initially seeded with the free electrons from Tesla discharge coil. These seed electrons quickly interact with the magnetic field of the coil and gain sufficient energy to ionize argon atoms by collisional excitation. Cations and electrons generated by the initial Tesla spark are accelerated from tip to the torch. Reversal of the direction of the current in the induction coil reverses the direction of the magnetic field applied to the mixture of atoms, ions and electrons. The fast moving cations and the electrons, known as the eddy current, collide with more argon atoms to produce further ionization and intense thermal energy. A flame shaped plasma forms near the top of the torch. Temperature in the plasma ranges from 6000 to 10,000 Kelvin. Direct current plasma sources. In direct current plasma sources, a high velocity inert gas produces high temperature plasma and separates the excitation energy from the analytical observation zone. In a typical DC arc discharge, the current density and energy available for atomic excitation are independent of the arc current. If the current is increased, the cross-sectional area of the current path increases proportionally, but with no increase in the arc temperature. The high velocity gas used to reduce the size of plasma is also useful in separating the current channel from the observation zone. A direct current plasma requires about 1 kilowatt of power and consumes about 8 liters per minute of the Wheeler's grade argon. Introduction of liquid samples into plasma sources. Liquid sample introduction is equally important in the plasma method. In all cases, the analysis can be only as good as the sample introduction. However, optimum conditions for the sample introduction into plasma sources differ markedly from those for the flame atomic absorption sources. Hollow cathode discharge lamps as emission sources. Hollow cathode discharge lamps are widely used as radiation sources for both atomic absorption and atomic fluorescence spectrometry. Their use in atomic emission spectroscopy has been limited despite some attractive characteristics. The hollow cathode lamp consists of two coaxial cylinders. The inner graphite cylinder is the cathode and contains the sample material. The discharge material is helium. The radiation is emitted from the negative glow, which is confined to the cathode cavity. These lamps are often used to determine the elements with low boiling points in high melting point matrices. The glow discharge lamp is similar to the hollow cathode discharge lamp, differing only in the position of the sample. The sample is not placed in the middle of the lamp but rather becomes one of the outer surfaces that seal the lamp. Atoms are released from the sample surface by cathode sputtering. Atomic emission spectrometers. In the emission spectrometers, the sensitivity is limited by noise originating from the two major components, the flicker of the source and the dark current of the photomultiplier detector. Since the dark current noise remains constant, it is important to decrease the source noise of the spectral background by decreasing this signal band pass until either the detector noise predominates or the spectral line width is reached. High resolution, high luminosity monochromators are necessary to isolate the spectral line from its background without the loss of the radiant power. Both concave and plane diffraction gratings are used as dispersive elements. A concave grating has focusing as well as a dispersing capabilities. It requires no additional optical components, whereas the plane grating requires one or more lenses or mirrors to focus the image slit onto the focal plane. Another optical device is the Eschel grating system, which is capable of resolution and dispersion an order of magnitude greater than the conventional grating of the equal focal length. Concave grating instruments. The spectrometer used for non-scanning multi-element analysis. It has concave holographic grating mounted in a Rowland circles configuration. In this configuration, also known as Paschen-Runge mounting, the entrance slit, grating and focal plane lie on the circumference of the Rowland circle. The grating is only optical component between the entrance and the exit slits. Positioning of the photomultiplier tubes external to the spectrometer housing reduces secondary array clutter and avoids secondary array scattered radiation. The secondary optics consist of mirrors positioned behind the exit slits which project and focus the radiation onto the cathodes of the photomultiplier tubes. For most determinations, only one array of slits is used. However, for extended analysis of up to 60 elements, a second array of slits lying on the circle directly below the first is available. It covers a spectral range of 225 to 625 nanometers. Plane grating instruments. Plane grating serves only as a dispersing element, and therefore a pair of concave mirrors is usually required to image the entrance slit onto the focal plane. Different spectral regions are focused on the camera detector film or different wavelengths on the exit slit by rotating the grating. A device known as Cinebar drive is used to obtain rapidly accurate linear wavelength readout of the position of the spectral lines on the focal plane. The Ebert mounting is used in almost all large 3M focal length spectrometers that contain plane gratings. This mounting is nearly stigmatic and achromatic, so that the light of all wavelengths is brought to focus on the detector without changing the detector to mirror distance. Echelle spectrometers. Echelle's grating provide excellent dispersion and resolution over the wide range of wavelengths in a relatively compact instrument. The different orders appear in horizontal lines, while the longer wavelengths of the lowest order appearing at the bottom and the highest order at the top. Here, the prism cross dispersing element separates the wavelength in the vertical direction, while the echelle grating separates them horizontally. Each line is equivalent to a segment of conventional high resolution spectrum, and successive lines are adjacent segments. The free spectral wavelength covered by one order varies from 1.8 nanometer at 200 nanometers to 11.1 nanometer at 500 nanometers for the echelle grating with 79 grooves nanometer. Detectors and readout devices. Detection used in emission instrument systems fall into two categories: photographic emulsions and photoelectric transducers. Most recently, mass spectrometers are being used as detectors for ICP sources. Emulsion have the advantage of integrating impinging radiation over the entire time of exposure and recording all spectral features simultaneously over a wide range of wavelengths. These characteristics allow weak spectral lines to be detected by using long exposure times, and they also provide a relatively inexpensive means of obtaining permanent records of emission spectra. Limitation of emulsions are long exposure times, the need to process and analyze the spectra, non-linear response to radiation intensity, low precision and sensitivity in quantitative determinations, and limited dynamic range. Photographic detection. Photographic materials consist of light sensitive emulsions coated on a glass plate or plastic film. The emulsion contains light sensitive crystals of silver halides suspended in gelatin. On exposure, the silver halide crystals that receive radiation from the latent image. Subsequent chemical treatment converts the exposed silver halide crystal into a black deposit of silver at the site of the latent image. After development, the emulsion is fixed in the solution that dissolves the unexposed silver halides. Finally, the photographic material is washed thoroughly to remove the chemicals used in developing and fixing. The entire series of operations follows rigidly controlled conditions with respect to time, temperature and chemicals. Photoelectric detectors. Since the radiation involved in the atomic emission spectroscopy lies in the visible and ultraviolet regions of the spectrum, the photomultiplier tube and the junction photodiode are the two transducers used almost exclusively in the current AES instrument systems. Photodiodes are used in applications where the detection of low radiant power is not required. The exit slit of the monochromator must isolate radiation from the individual lines by precise positioning of the slit and the accurate control of the slit width. Alternatively, a more complicated mirror system within the spectrometer may be used to sequentially focus radiation of varying wavelengths into this exit slit. The radiant power of the spectral line that impinges on the slit is converted by the PM tube into current that is then used to charge the capacitor resistor circuit. Two modes of integration are used to average the PM signal, both with the integration time of 25 to 40 seconds. In older method, the capacity voltage is the quantity readout. The voltage across the capacitor at the end of the sampling time is the function of the accumulated charge. Thus, the capacitor voltage is proportional to the time integral of the radiant power. The powers are now compared with the operational amplifier circuits that outputs the voltage ratio from the two lines. In integration with the constant time, a voltage to frequency circuit is used to convert the capacitor voltage into electrical pulses of equal height. But counting the pulses generated during the integration period, the number proportional to the radiant power is obtained. This measuring technique has the advantages of various dynamic range, extending over 6 decades and built-in noise reduction. The output is usually in the digital form, ready for computer processing, direct reading. Computerized spectrometers are usually calibrated with high and low concentration standards. Mass spectrometers. The mass spectrometer system used for the purpose can both process data and generate reports. The detection limits for many elements are significantly lower than those observed for ICP AES systems with the photographic or photoelectric detectors. ICP MS system also permits the determination of the isotopic composition of samples. Instrument configurations for multi-element analysis. Detection systems used for the multi-element analysis are either sequential or simultaneous. In the former system, dispersion radiation is transmitted sequentially to a single detector. This is generally accomplished by scanning monochromators or rotating filters. Scanning monochromators have a grating or a mirror usually controlled by computer-driven stepper motor. Linear scanning, rapid slewing to preselected wavelength and manual operations are possible with these devices. The most common simultaneous or parallel systems are multi-channel with one or more detectors for each analyte element. The multiple PM tubes positioned on the circumference of the Rowland circle, the PM multi-channel module used with an Echelle spectrometer and the linear photodiode arrays are example of the simultaneous detection system. Multi-element simultaneous analysis is used effectively in situations that require routine determinations. Instruments used in such analysis, sometimes called as quantometers, have widespread applications, especially in the ferrous metal industry. For less routine analysis involving greater control of optical parameters, instruments with greater flexibility are required. If sample sizes are adequate, sequential multi-element instruments provide the flexibility needed. The sequential system employs a double monochromator to minimize the interference from the stray radiation. Computer controlled stepper motors provide fast movement of the grating to the desired wavelength. The plasma plume observation height is optimized automatically for each element by moving mirror M1 and lens L1 is tandem. A monochromator enclosed in a vacuum is used to determine sulfur, phosphorus and boron in steel in the vacuum ultraviolet at 190 nanometer region of the spectrum. Although the conventional ultraviolet region of the spectrum usually provides the best analytical lines for the phosphorus and boron, common components of steel interfere spectrally with both of these elements in this region. Applications of atomic emission spectrometer. AES can be used in the following: analysis of ferrous and non-ferrous alloys, determination of trace metal impurities in alloys, metals, reagents and solvents, analysis of metals in geological, environmental and biological materials. Water analysis ICP instruments have been coupled with mass spectrometers to provide a powerful analytical technique. To summarize, atomic emission spectroscopy AES has long been a standard method for metal analysis. In atomic emission spectroscopy, a minute part of the sample is vaporized and thermally excited to the point of atomic emission. The energy required for these processes is supplied by an electric arc or spark, or more recently by a laser or plasma composed of inert gas. It is convenient to distinguish these sources from the chemical flame sources used to obtain emission spectra. Instrumentation of AES may be divided into three major components: a sampling device and source, a spectrometer, and the detector and the readout device. AES may be used in the analysis of geological, environmental and biological materials, and also water analysis ICP instruments have been coupled with the mass spectrometers to provide a powerful analytical technique.